Dear students, welcome to this module Digital Communications EN3009J. So this is the first video lecture under this module. Those of you who have attended my microcontroller module last year, they all know me. I am Abhishek Nag, and this year I will be teaching you digital communication and wireless communication. So let us start with the digital communication module. Unfortunately, we couldn't be in Beijing this semester in front of you teaching face to face. So we have to go fully online this semester, and there will be some difficulties, or some things will be totally different this semester than the previous ones. So I will be telling you as time progresses what are the things that will be different this year, and I will be helping you throughout this semester because this semester is different, and we are going for a totally online delivery of the modules. So there will be few changes for sure, and I will tell you as time progresses. So let us proceed. So this is the overview of this module. The topics that will be covered under this module is random variables and random processes. So we will start with a bit of introduction to probability theory and random variables and random processes. You have probably gone through these concepts in your maths class in maybe first year or second year, but we will revisit some of these concepts because it's very important in the digital communication module. Then we will go through optimum receiver for binary data. We will go through baseband transmission. We will go through passband transmission, signaling over band limited channels, and then some advanced topics in information theory and coding and OFDM. So you will get to know and learn in details about all these topics as the module progresses. And this semester, since we are going through a fully online delivery, we will be having a full continuous assessments for this semester. So you will have a few MATLAB assignments which will count towards 40% of your final grade, and you will also have a lot of continuous assessments in the form of quizzes, mini projects, assignments, and that will count for 60% of your grade. And I will announce on Brightspace or through other forums. I have not decided yet, but you will get to know, like through emails or Brightspace, or maybe through WeChat or other formats. I will announce the exact pattern of these quizzes, these mini projects, or these assignments that I'm planning to do this semester, and you will get notifications, and also how these assignments and assessments will be conducted. So moving on, the grade scales that I'll be using this semester is the alternative numeric scale. So this is the one that I'll be using, where 40% and above is pass, and for getting an A you have to score more than 90%. For an A plus you have to score more than 95%. So this is the scale that I will be using for this module this semester. About the textbook, so there are very good textbooks available. The one that I will be following mostly in this module is the one by uh, Dr. Ha Nguyen. This is the book which is the first course in digital communication. So this is the main textbook that I'll be following, and you are encouraged to follow the reference books by Simon Hekin and John Proakis. So these books are a bit advanced in its treatments, but the book by Ha and Nguyen, which I'll be following, is much easier to follow, and I think you will get a copy of this in the internet. There is a free PDF of this book. You can also get it from your library if that can be arranged. And my lecture notes will be more than enough for this module, but since again this semester things are different and we are following fully online delivery of the modules, I would encourage you to consult one or many of these books that are available, because this semester things will be different, and you will be doing a lot of self-learning. So these books are strongly encouraged this semester. I will be there to help you. We will have tutorials, we will have live sessions with you to discuss your doubts, but maybe there will be some gaps as I am not physically there to address your doubts. I think the books can fill up those gaps pretty well. So that's about the books. And as usual, plagiarism is a serious academic offense according to UCD policies and BDIC policies. So you are strongly encouraged not to be involved in any form of plagiarism during your continuous assessments, and all the MATLAB assignments that you will be having. So please stay away from any form of plagiarism, because the consequences are going to be very serious, and you might fail the module, or you might lose grades. So please don't get involved in this. So starting with the basic concepts now about the digital communication. So we are studying digital communication, and the question would arise that why would we study digital communication? So so you have probably studied analog communication in your stage 3, and in this stage 4 you are studying digital communication. So the main difference between analog and digital communication is this. So you have a signal. Let's say you have an analog signal which varies smoothly with time, and then you have a high frequency carrier. So this is the carrier signals that you have, the one that is varying very frequently, and then you have the actual signal which is getting modulated by this high frequency carrier. So basically the purpose of this high frequency signal is to carry the information bearing low frequency signal. So imagine that you are throwing a piece of paper, you are writing something on a piece of paper, some message, and throwing it to your friend. You want to convey some message to your friend who is sitting 100 meters apart from you. So if you just throw the piece of paper, it's very light and it may not reach your friend due to the friction of the air and so on. But imagine that if you wrap the paper over a heavy piece of stone and then throw it to your friend, then it will probably reach your friend who is sitting 100 meters apart. So that's the whole concept of modulation in communication systems. So you are basically trying to send the low frequency signal, which is this particular signal, that is the low frequency signal, and then you are basically modulating it to facilitate the delivery of this signal. So basically the modulating signal, which is this one, the high frequency signal, is behaving as the piece of stone, and it's helping the signal to get carried forward. So this is the concept of analog signal, which is smoothly varying over time. But in a digital signal, the variations are abrupt. So you can see that it basically follows a few set of levels. So let's say a high level and a low level, or ones and zeros, as they are represented digitally. So this is the signal, and then similar to the concepts of analog modulation, you are modulating this digital signal with a high frequency carrier that is varying very frequently with respect to time. So this is the difference between analog and digital modulations, and the reason why we do digital communication is because these digital communication systems are more advantageous in the presence of noise. So let's say you have a signal which is a clean signal like this, and the clean signal is modulated over a high frequency carrier. Now in every communication system there will be some noise. So as you see in this figure, you have noise added to the signal, and the signal is getting distorted. So here if you see the variations in this region, you will see that the variations in the signals are almost getting wiped out by noise, because the variations in the signal in this region is low, and the variation in the signal, let's say in this region, is high. But in this region, the transitions between the different levels of the signal is very low, and the noise can impair this region very much, and it will be very hard for the receiver to detect the levels of the signal in the presence of noise. But in case of digital communication, you see that the levels are quite distinct, and they are separated apart by a margin here. So the 0 and the 1 is separated by quite a bit of margin, and because of this, even under the presence of noise, as you see, you can still distinctly distinguish the signal in the receiver, like this is your 1 and this is your 0, because the gap between the 1 and 0 is quite distinct, unlike the analog communication system, especially in this particular region where the gap is not so distinct. So that's why we prefer digital communications over analog communication. And there are many other reasons also for doing digital communication, because most of the modern systems are digitized, and you are storing information in computers which are in digital form. So the data that you are transmitting over a communication channel are in general digital in format, so it's easier to transmit that data digitally. So that's why also we would do digital communication, and that's the whole motivation behind using digital communication. Also, there in this slide you can see that if you have a digital signal, which is this one, the original pulse, and as it travels through the channel, it gets distorted. So there will be some distortion, there will be noise added, as you saw in the last slide, and then the signal itself gets faded as it goes through the channel. It gets attenuated. Okay, so the amplitude of the signal goes down because it gets weak as it travels through the channel, and then it gets degraded, and up to a point it will get severely degraded. And digital communication, since as you saw in the previous slide, it has some finite levels like zeros and ones. So basically the signals in digital communication belong to a finite set of waveforms. So this is very important. So in digital communication, the signals, the signals belong to a finite set of waveforms. So that is why the signals can be easily recovered to its ideal shape, and all the noise and the distortions can be removed, because you know that the signal just belongs to two levels, zeros and one. When the signal is getting distorted like this, you probably know that this is the high level, this particular peak is the high level, and this is the low level, and then you can regenerate the signal to its original shape between 0 and 1. So this is what is meant by saying that in digital communication the transmitted signals belong to a finite set of waveforms. But in analog communication, as you saw, the levels of the signals are many. So if you go back to the previous slide, you can see that the levels of the signals varies smoothly between many levels. So that's why you can say that in analog communication the transmitted signals are analog waveforms, and that can take infinite variety of shapes. So that's why it's a bit difficult to regenerate the signal accurately to its original form. So that's another advantage of digital communication that you have. So in a general digital communication system, you have this essential blocks. So you have a source or a user which is actually generating the message, and then that message is getting transmitted by a transmitter, and the message goes through a channel, and that channel transmits the message to the receiver, and finally the receiver decodes the message and then it sends to the final user. So you have a source and a sink, and then in between you have a transmitter, you have a channel, and you have a receiver. And inside the transmitter you have again further blocks. You have the source encoder, you have the channel encoder, and you have a modulator. And inside the receiver also you have the opposite functionalities. So you have a modulator in the transmitter, so you have a demodulator in the receiver. You have a channel encoder in the transmitter, so you have a channel decoder, and then you have a source encoder in the transmitter, so you have a source decoder in the receiver. And then there is a requirement of synchronization between the transmitter and the receiver, and the synchronization block is only present in a digital system. So in this module, we will go through the different aspects of this digital communication system. We will go through the different blocks in the transmitter, we will go through the different blocks in the receiver, and we will study them in detail. We will also study a bit of the channel, but we won't study the synchronization part in this module, so that is beyond the scope of this module. That is a bit advanced topic. So I think I have covered most of these advantages of digital communication, so digital versus analog. As you saw, digital signals are much easier to be regenerated. Digital circuits are less subject to distortion and inference. Digital circuits are more reliable and can be produced at a lower cost than analog circuits. It is more flexible to implement digital hardware than analog hardware. And then digital signals are beneficial from digital signal processing techniques. But on the other side, there are a few disadvantages also. You need some heavy signal processing because ideally in the real world, most of the signals are analog in nature. Like as I am speaking, my voice, if you represent it through a signal, it's basically analog in nature. So you have to convert this voice signal to digital domain, and then to do that you will require a bit of extra signal processing. So that's a disadvantage because you need heavy signal processing. Synchronization is very crucial in digital systems. So as you saw in the block diagram in the previous slide, larger transmission bandwidth is required for digital systems, so that is a disadvantage again. And non-graceful degradation, so the hardware degrades very sharply in digital communication systems, so that is another disadvantage. But you can see there are more advantages than disadvantages, so that's the whole point of studying digital modulation, digital communication. So, having said that, we will go through the probability theory, random variable, and random processes, and so this is the more technical part of the module, and we are going to enter there. So this is very preliminary concepts I have covered for probability theory. I am assuming that you already studied probability theory in your earlier classes. So I will encourage you to go and revise the concepts of probability theory, random variables, and random processes, because you will be needing a lot of it in this module. So so let's go through some of the basics. So why probability theory is needed? So the main objective of a communication system is the transfer of information over a channel, and most of this information carrying signals, they are random in nature, so they have some uncertainty associated with it. And you will study in the later stages of this module that if the signal is not uncertain or not random in nature, then it does not convey any information. So from a theoretical perspective, from a mathematical perspective, if your signal that is communicated over a digital communication system, if it has to convey an information, it has to be random in nature. And to model that randomness or to study the properties of that signal, you have to appreciate the theories of probability, the theories of random processes. So that's why we should study a little bit of probability theory and random processes while we are we are starting to study digital communication. And then in the communication channel itself, there are a lot of imperfections. So there are noise, and there are fading, and there are interference, distortions. So all these are again very much random in nature, and therefore to better appreciate the properties of this noise and the imperfections, and to model them properly, you have to apply the concepts of probability theory and randomness. And then we are concerned with the methods used to describe and characterize a random signal, generally referred to as a random process, also commonly called stochastic process. So in essence, a random process is a random variable evolving in time. So so most of your signals and noise and all these things in digital communication systems are random in nature, and they are time varying random variables. So they are basically examples of random processes, and to understand them properly, you have to revise the concepts of probability and random processes. So so to begin with, the very basics of the probability theory. Some of you might recall this from your previous modules which you have done. There are few keywords that are associated with probability theory. So the first thing is random experiment. So basically, a random experiment is an experiment whose outcome for some reason cannot be predicted with certainty. For example, you are throwing a die, or you are flipping a coin, or drawing a card from a deck of cards. These are all examples of random experiments, because if you flip a coin, you can say that with 50% probability or 50% chance there can be a head or a tail, but you cannot definitely predict whether it will be a head or tail. So that's the very subtle difference. So that's why it's called random experiment. Similarly, when you throw a die, you can say that it can be either 1 or 2 or 3 or 4 or 5 or 6, but you cannot definitely say that what will come when you throw a die. Then comes the concept of sample space. So basically, this is a set of all possible outcomes of a random experiment. So this is denoted by omega. Outcomes are denoted by small omegas, and each small omega lies in the capital omega. So basically, sample space is, let's say, if you consider the flipping of a coin, then it has two outcomes, either a head or a tail. So your small omegas are head and tail, and your sample space consists of these two cases. In case of a die throwing, you can have 6 outcomes possible, and your sample space consists of all these 6 outcomes. So a sample space can be discrete or continuous, so we will get to that later. What is meant by a discrete sample space and a continuous sample space. And then there are events which are subsets of the sample space, for which measures of their occurrences called probabilities can be defined or determined. So let's say if you have this die throwing experiment, so it has 6 outcomes, and each of those 6 outcomes are events. So what is the event that one occurs when you are throwing a die? That has a probability or a chance of occurrence of 1 over 6. Out of all the 6 total outcomes, there is 1 over 6 chance of getting a 1. Similarly, there is a 1 over 6 chance of getting a 2, and so on. So these are the subsets of the sample space for the die throwing experiment, and these are called events. So, and then there are these 3 axioms of probability. So, so for a discrete sample space, you define a probability measure P on the entire sample space as a set function that assigns non-negative values to all events denoted by E in capital sigma, such that the following conditions are satisfied. So there are 3 axioms, which the first axiom says that your probability of an event E should always be within 0 and 1. So on a percentage scale, probability ranges from 0 to 100%. So if you now go to axiom 2, then that says that if you take the probability of the entire sample space, sigma, then that will be equal to 1. And the axiom 3 says that for mutually exclusive events, E1, E2, E3, we have the probability of the union of all those events is actually equal to the sum of the individual probability of those events. So I will stop here for this lecture, and we will resume right from this part in the next lecture. Thank you very much.